All right, so let's get started. Hi, I'm Badrish from the database group at MSR, and today it's my pleasure to invite Karthik Ramasamy, who is here visiting us today. He is basically the co-founder and creator of this startup called Streamlio that focuses on building next-generation real-time analytics pipelines. Before this, he has been in the streaming community for a long time, particularly at Twitter. He was basically leading the real-time infrastructure group there, and he co-created popular systems like Heron. And he has 2 decades of experience in basically these kinds of big data infrastructure and streaming and parallel databases and all. So today we'll be hearing about more about his startup and how he's using Apache Pulsar. So take it away.
Sure. Thanks, Badri, for the introduction. Can you hear me? Or the mic is not on, I think. Is it?
It's okay. It's okay. If there's a problem with the audio, Matt will come out.
Okay. Okay. Yeah. So thanks for the Badrish for hosting us, and I'm glad to be here. I think I have some good relationship with Microsoft because I know quite a few folks. Like Phil, and I did work on some of the ACM SOC conference, and I know Raghu, then I know Surjit. So quite a few of the database folks that I used to work with are all here. So anyway, so I'll be talking about Pulsar in general. Pulsar is a completely open source project that was done open sourced by Yahoo and has been in production for 4+ years at Yahoo. And then now a lot of companies have started adopting, like 25+ companies have already adopted Pulsar. So we use Pulsar as a base for building things as a core, and Pulsar is the core center of what we do at the Streamlio. So I'll be more focusing on Pulsar because it's a very interesting technology. So just to give a preamble in the talk, so we are increasingly in a connected world in the sense like a lot of devices have some connectivity in some form, like in terms of wearables and IoT devices and and healthcare related devices. So all these are going to produce a lot and lots of data. And this is kind of a well-established fact that the data is growing at 40% every year or some on those lines. So this generates more streaming like data, which means like each devices that the data that generates, or even the manufacturing facility in a factory floor or even an oil rig, they are generating a lot of data in the form of streams when the data is continuously being monitored for certain defects, for preemptive, proactive asset maintenance, and all those various applications. So that's one of the reasons why data stream processing is becoming very vogue these days. So you talk about a lot of data processing in the streaming fashion. And what is the thing that PO experience and what are the market perceives? I will combine some aspects of business with technology aspects. It's not going to be a pure technology talk, but if you have any questions, feel free to ask me. So what is stream data processing? So here the key thing is those events are analyzed and processed as they arrive. So if you look at the value of data over its time, so it's the highest value of data is only when during the time of its production. Now the instant the data is produced, it has the highest value. As the data ages, the value of data goes down as you go into minutes and hours, then you get into more into batch processing kind of aspects, right? So because of the fact, if you are analyzing the data very timely and contextual, as soon as it is produced on fresh data, it can be more useful. So because of the fact that you're making decisions based on the fresh data, the decision latency also eliminated because of the fact you're acting critically. One example that we can give is take the example of a Super Bowl, and based on a team touchdown, like let us say like San Francisco 49ers did a touchdown on that game. Then immediately there is a trend of tweets going around in terms of, hey, people discussing that was an awesome touchdown and you could have done this way, done that way. Then how can we exploit the trend in order to inject 49ers related jerseys and all the various things, right? Because this is an ongoing phenomenon that changes in a continuous fashion, right? So, and this decision has to be automated in certain ways so that we can see the trend about 49ers being chatted about quite a bit and inject appropriate ads into that. So again, like in streaming parlance, people call this as a data in motion analytics as well. So what are the broad category of application patterns that we have seen from a streaming perspective? I mean, so far from my experience, these are the various patterns that I have seen. If you have other patterns that you have seen, please feel free to share. So monitoring, a broad set of monitoring anything like monitoring logs coming from systems, or monitoring data coming from an IoT device, or monitoring some hot device which is spewing the number of beats per second. So monitoring in general is a broader theme of streaming pattern. Another one is from a microservices as well. So microservices also where the data is continuously coming in the form of, let us take an e-commerce application, and the data comes in, and you can consider the e-commerce request as a stream as well, and the request has to be processed in some form, right? And that also could be done in a streaming way, but not from the streaming that way we have understood. People consider that also as a streaming because data comes in, data processed, doesn't mean that you are doing aggregation, join, and all the various things, but data is processed as they arrive. If the definition of that is the definition of streaming. Then workflows. So
say OLTP kind of work.
So the difference is when a request processing doesn't mean it's always generated transaction. It could be saying that, for example, let us say I wanted to do a tweet. Now, whenever I give a tweet using an REST API, then it has to go through multiple steps, which is actually multiple microservices, right? The first microservice is verifying whether I am a real Twitter user. Then after that, I have to save the tweet in some form. Then after that, I have to make sure that the tweet is queued up into my followers, right? So these are all individual microservices, right? So one request is going through these multiple microservices as a staging kind of equivalent, right? So we can call it as a streaming processing from that perspective. Okay. So then the next one is workflows. I mean, the differentiation from these monitoring and microservices and the workflows is that typically the duration of processing on that individual step in the workflow is a little bit higher than the processing that you do in the microservices or the typical streaming where you're in millisecond or a few seconds, whereas in workflows it can take a little bit more than that. Again, the people also consider as some form of queuing/streaming, where the data is coming in and you do some stage of the workflow. For example, let us say the tax workflow. So when the tax document comes in, first of all, you validate whether all the fields are filled up. Then it goes to the next work queue item, which again says what this income is, this minimum tax that is being paid or not. So those kind of is a workflow kind of these things that you can stage. And again, that might be including image recognitions and all the various things like that, because you are extracting from the document or a photocopy of the document itself. Then of course, everybody knows about stream analytics. I'm not going to, because that's one of the driver for the entire streaming itself. Then the next one is more of a model inference as well. So model inference in the context of, for example, you build all these ad models, machine learning models based on user profile in the batch world. Now, as the data is coming in and you wanted to serve the appropriate ad based on the user profile and everything, that could be like essentially a model inference in some form. Again, that is considered as a simple stream processing kind of, where data comes in, look up that model, or probably look up multiple models before you say, okay, this is the right ad to serve at that point in time. So model inference and the serving. So if you look at the underlying theme of all these various individual applications, the often from a technology perspective or from underlying what it needs is like you need some form of data ingestion into the streaming engine, whatever it is. Then you need to do some kind of a durable ingestion, which needs storage as well. Then you need to compute on the data or act on the data in some form. And that is where the compute comes from. And that is where the compute comes. And after compute finishes it stores the data into some kind of result storage so that you can serve the results out. And compute you also can use the storage for intermediate state or checkpointing and all those various other purposes as well. So now, one of the challenges that we face in the streaming world today is all these are different systems today. So messaging is one system, storage is another system, result storage is a separate system, computer another system. So because of that, the barrier to adopting streaming in a company has grown bit high because of the fact that people require expertise in different systems, and then you have to glue them together in some form. And the programmers or even the users are exposed to the brunt of the several APIs that they have to learn, that the learning curves become harder, and learning multiple systems become much harder, and operating these things at a much harder pace because you need multiple system admins and DBAs and all the various stuff, which means the business value of the streaming to establish why streaming that I have to use becomes a challenge. So now the question is, can we simplify this and doing it in a single system and make the cost of streaming so cheaper and easier to use so that it can be ubiquitous? So that is what our mission is, and that is what we are going to do. We are attempting to do that actually in Pulsar. And so simply put, Pulsar is nothing but a flexible messaging / streaming system backed by a durable log storage. That is the one line if you want to talk about what Pulsar is. So what distinguishes Pulsar from the rest of the pack is the ability to separate serving and storage. So Pulsar has this notion of broker, which does the data serving, and the storage nodes are called bookies. And bookies are the ones which store the data into storage and access the data whenever it needs to. So whenever a producer comes in, it gives the data to the broker, and the broker in turn sends to multiple bookies for replicas, replications, and all those other purposes. And the bookies in turn store the data. I will go into detail of each steps in subsequent slides. Now the key thing is you can because of the fact that it's serving and separated from storage, you can scale them independently. So if your storage requirements are increasing, you can keep adding storage nodes into the system, and it will keep on filling those new nodes, right? Similarly, if there is a need to increase your storage needs, you can add the broker separately. So that means you can do asymmetric serving, smaller amount of data, large amount of serving. For example, in Twitter context, our intake was 400 terabytes of data every day, but the serving was around 20 petabytes because several applications are using the same data again and again and all the various stuff like that, right? So that is an asymmetric. Similarly, the other side asymmetric is small amount of serving, but you wanted to keep the data for a longer time. So that way, you have more storage but less amount of serving. So all these combinations are possible in Pulsar. So as I said, broker is the only point of interaction for clients from a producer and consumer point of view. Brokers acquire ownership of something called topics. So the Pulsar has this concept of, I will cover that in the multi-tenancy slide, as a concept of what you call tenants, which are all teams that you can be onboarded. And then within tenants, there is a notion of namespaces, which means any team can have multiple applications. And within the teams, you can have these multiple streams in the form of topics, right? So you can organize it like that. So the brokers, especially some brokers have the ownership of a particular set of topics that they serve and produce the data into, or topics or the topic partitions essentially. So brokers have no durable state because even if they die, the state can be recovered from the underlying storage because all the data is right through. And brokers, all they have is cache and some kind of load information that they exchange, which they can reconstruct anytime. So which means that is a very resilience from a broker point of view. And also it provides a service discovery mechanism for a client to connect to the right broker. So in the sense I can connect to any broker, any client that comes in can connect to any broker. That broker, if the client says, I am interested in the topic X, then if that broker is not serving the topic, it will automatically redirect to the right broker so that the appropriate broker will be connected and it will be serving the data or producing the data into the topic. So that way you don't need external load balancer or anything like that. So automatically the discovery mechanism is provided. That also means we can do some kind of load balancing as well, where the ownership can dynamically change during system maintenance time or during loaded time and all the various time. So So that is a service discovery mechanism. So to give an idea about how the whole thing works from a topics and a broker interaction point of view, a topic can have multiple partitions because of the fact the sheer size of the data that you might be ingesting might be high. And you can, we support in Pulsar key-based partitioning, hash-based partitioning, round-robin partitioning, and also range partitioning. And so the topic 1 partitions, topic 1's partition 1 and partition 2 are distributed across multiple brokers, broker 1 and broker 3. And so anybody is interested in producing into the topic 1 will be contacting those 2 brokers, establish connection, and depending upon the partition criteria, they'll redirect to the appropriate connection so that the data ends up in the appropriate partition. So similarly, consumers consume data using a subscription. So in order to consume data, you need to have a subscription, and that subscription could be of different types of subscription that I will cover in the later slides. And then there could be multiple consumers on the same subscription, and then the data will not be deleted until all the consumers of all the subscriptions on a particular topic is consumed. Then only data can be erased. Or if you wanted to choose the data for infinite retention, you can do it as well. So now let us see, like the notion of from a consistency point of view, whenever you start with, you configure how many replicas you want for a particular topic, right? So then when the producer sent first data, the broker sends the data to that many replicas in parallel and make sure that the bookies store the data. And when the bookies have given an acknowledgement to the broker, then only we send the acknowledgement back to the producer saying that, okay, like your data is safe right now. And you can even configure the number of acknowledgements that you want to wait before the broker gives the acknowledgements to the producer. For example, in this case, we are configured with 3. You can even do 2 also. So 2, even 1 is possible, but depends on the level of this degree of consistency that you would like. So then from a durability perspective, the storage nodes, the bookies, have this notion of a journal. So that way what happens is like we can do fast writes. So you have each of the bookie nodes have this journal, and every message that comes in is all F-synced, probably doing a simple group commit or a batching based commits. And once it commits into that set of a journal, then the acknowledgement is issued right away. So it also, in the next slide, I will cover a little bit more detail on that functionality. So when when the bookie gives the acknowledgement, it's automatically F-synced, and the broker can send the acknowledgement. By the time broker sends the acknowledgement to the producer, your data is not only durable across all the bookies, it's also replicated. So from yes.
So in that architecture on the previous slide, so you clearly have a separation of the compute and the storage, right? But can the broker connect to a different backend storage? So let's say I want to connect to a cloud storage.
I'll come to that. There's a slide for that.
Okay.
There's called a tiered storage, yes.
Okay.
Yes.
Also, you said the broker is doing the replication, but you also said the broker is stateless. So what happens if one of the copies is not responding and it needs to
Good question.
do some kind of failover later?
Yep. So what happens is the broker does not have the notion of state. So how does the broker, there is a broker essentially has a client that is connecting to the bookies, right? Broker sees only in the messages in the form of log entries. Like this is my topic and this is my entry, go and write it. So underlying there is a bookie client, which is a library that we link with, and that in turn does all the magic of replicating to the multiple bookies now. Now what happens if a bookie goes down, right? So now I have one detailed slide there. So what happens is essentially like the bookie closes the current ledger because so you can think about topics as a set of finite ledgers. So when the current one bookie goes down, the current ledger is closed because that is whatever the last messages have been returned. The new ledger is open on a different set of 3 nodes. So you can still use, let us say the top bookie is down, we can still reuse the current set of 2 nodes. The third node, which is available, whichever is available, it can pick it up and open a new ledger on those and continue to write that.
So if you lose one replica, you're going to just close down the entire replica set? No.
No. So like what happens is like there is a recovery process that picks it up. For example, let us say that bookie has gone down, which means all the data that has been residing on that bookie's replica factor has gone down by 1, right? So there is a what you call a background process called a recovery process that runs what we call a many-to-many recovery process. So it knows, there is one piece that is missing in terms of here is, there's a zookeeper involved everywhere. So that keeps track of what bookie is storing, what segments of data, right? So by looking at the segments, what segments have been, replica has been lost, then many-to-many, the bookie recovery process will make sure you copy those segments from these different nodes into a new set of nodes. So that's in the background, it happens automatically. But remember, 2 replicas are still online. Third replica is lazily being copied. Okay, so from an isolation point of view, like especially in a Pulsar-like system, there are 3 different type of access patterns, or not access patterns, and patterns of read and writes. One is writes, complete writes that is coming through. Then there is tailing reads. Tailing reads means you're on top of the queue. The data, once it comes in, immediately you're consuming the data. That is called tailing reads. Then there is a catch-up reads. For example, some consumers might be falling so behind that they are not able to consume the data from whatever the tailing reads are. You have to go back to the disk in order to get the data from, right? So those are the 3 different patterns. Now, how does, so we isolate all these patterns in so that each one does not interfere with each other. In existing systems like Kafka, this is an issue. Because, for example, if there are 20 consumers consuming out of the same topic, if one of the consumer falls behind, it affects the other 19 consumers. The reason being the fact Kafka writes into page cache, and then if the consumer getting so delayed comes back and asks for older data, you have to go and get the data, put that into page cache, then serve it off. Because of that, you have to replace some of the existing new data. So you go into some kind of swapping behavior, and that affects the other 19 consumers. And this happened in practice at Twitter when we were using Kafka. People used to come and running, oh, my streaming topology is not running well, I didn't do anything and all. Then we will beat our head around it for several hours and other things. Finally, we figure out some next topology. Out of 400 topologies, somebody else will be lagging behind so much that hey, that topology is not consuming faster enough. So because of that, you ended up designing this such a way that the paths are different actually. So for the write path, you have the write cache, and the write goes into the journal. So then the journal gets flushed, acknowledgement goes into this. Then for the tailing reads, the broker itself caches the data. Remember the path that the producer comes to broker, then broker in turn sends the data to the bookies to store it. There's a write through all the way. Then broker also caches that copy of the data. Then moment an acknowledgement comes through, it sends the acknowledgement parallelly to the producer, as well as dispatches to the consumers, all the consumers, so that immediately the consumers can consume out of it. So even if you're lagging behind with a small amount, as long as you can read it from the cache, the tailing reads will be satisfied out of the bookies, so the brokers itself. Now, if you want to catch up reads which are so delayed, then the broker, if it does not have anything, then you will talk to the bookies, appropriate bookies, hey, give me this data. Then it will use the read ahead cache, which is that cache that is actually read from the actual ledgers and all the various underlying storage. Then it will populate the read cache, and that will serve the broker in turn will get the segments from those bookies and catch up on the right reads. So it's a completely different path itself. It's on-demand reads, think about that way, right? So that way, like all the 3 paths are separated so that it does not affect consumers doing at a different parts of the stream itself. So how does this data is stored underlying in the storage nodes? So we store the data in the form of segments. So essentially segments could be a few gigabytes depending upon the size and or time or whatever it might be. Or sometimes when a failure occurs, our segments or ledgers are the same terminology. So whenever some bookie fail happens, right, we close that segment or close the ledger, right, and start a new ledger. So now the segments, as I said, is sprayed on the underlying storage nodes. So the key is like as long as any K nodes are available, if you configured K replica to be available for each message, it will continue to function. So which means like the write availability of the system is pretty high. So because you don't, there is no notion of tying of a particular ownership to a particular storage, because segments keep shifting. On the metadata where the segment, which segment is occurring after what segment for a particular topic or a particular stream is sequenced in the zookeeper, right? So that way what happens is like the write availability of the system is very high in this case. So now let us take a look at one of the node failures. So which means all the segments in this particular node are lost, and as I pointed out earlier, there is a backup recovery process which in turn picks it up and copies those segments in the background process. Meanwhile, you have two replicas that is operational that can serve the catch-up reads, and you still have the broker which is still serving your tailing reads, and still the writes can happen because you can grab another node and keep writing into that, right? So once the replica factor becomes stable enough, then the system does not have a downtime at all during the background process. So that also and then another one advantage that you get off is seamless cluster expansion. So in Kafka world and all the various stuff, there is a notion of, I will come into one slide where what the Kafka legacy architecture, what has its problems, right? So the cluster expansion, adding new nodes and all these things is a breeze. Just add a new node and automatically the new segments are started using that, new segments will start using that as well. Doesn't mean it will use only that added node, but it will also add the new segments as well. So eventually what happens is as the segments retention period expires, eventually all of them will come to the same storage occupancy at some point in time. That depends on how often you expire the data as well. Then another cool property that we have is you can even configure a particular node that if it's 80% full or whatever it is, you can turn that particular storage nodes into a read-only. So automatically it will change its role to read-only. So which means it will refuse to accept any writes. Then the write path will happen is, oh, this bookie thinks that bookie will not accept any more writes, I'll switch to another bookie. The current ledger is closed and a new ledger is open, and boom, keep writing that thing. So that way it is a lot of operational capabilities are built into that whole mix. So now you come to the tiered storage, right? You asked me about this thing. So now, do you want to keep all the data in the hot storage? Because it could get potentially expensive, right? Because you have to keep on adding nodes and other things, right? So if you wanted to keep the data as much longer period retention or whatever it is, you can use a tiered storage, which is a low-cost storage, right? And the low-cost storage in the form of cloud means you have S3, Azure, and GCP or a GCS. Or it could be Hadoop also for low-cost storage, right? So in our case, all we have to do is configure that any segments which are older than this amount of time automatically gets propagated into a tiered storage. So all we have to do is we switch the metadata. For example, in the segment metadata that we have, the segment is found on these bookies. Instead of that metadata, once the segment is propagated to the low-cost storage, we just change it to this segment is in the tiered storage, and this available in this S3 bucket in this offset. That's all we have to do. So that way, like it's a seam.
So what's in the local storage? That's not a cache. So
This one?
So the
This is a hot storage.
So should I think of that as a cache, or it's the copies are?
This is a hot storage. This can be a permanent storage too.
It's also permanent.
Permanent, but we call it as a hot storage. Only when this is an optional thing. The tiered storage is an optional.
I understand, but I'm saying if once I have the tiered storage, then will a particular partition live either in cold or hot, or like can it live in both?
No, like the partitions, all the active topics and this partition will live in the hot storage, and the older data of that partitions or topics will move into tiered storage. So that again depends on the retention period. Let's say like you have 30-day retention, but I want to only live 7 days worth of data on this one. The rest of the 23 days worth of data can be in the low-cost storage, right? So it can be done. Or if you want like keep it infinite, you can do that as well.
So maybe a related question is, if you wanted to then do, say, query processing on the stuff that's in cold storage, do you first have to move it into hot storage, or do you
Nope.
do it directly on the cold storage?
Nope. So because of the fact that the broker knows where to read that segment from, you'll pick it up from the underlying tiered storage, the low-cost storage directly.
I see.
Because like, so that's why when you replay a stream, for example, since you have some amount of retention, depending upon whatever the retention, you can slot in a particular time. Like let's say from time T1, replay all the data in that stream, right?
Yeah.
So then depending upon where the segments are, it'll pick up the segments from that low-cost storage or hot storage and serve that segments to you. Yep. So now partition versus segment, why should you worry about it, right? So if you look at in Kafka and all, each partition is a single entity. A topic and its corresponding partition is an entity completely unknown, and each partition is tied to a particular disk. So like one primary, another one is the partition copy, right? So now, so which means your storage size of a particular partition is restricted by the size of the disk that you map into. So now if you wanted to, your partition is growing, then you have to do expensive rebalancing. You have to repartition the data on all the various things like that, right? So that is one of the biggest challenges in Kafka itself, right? In our case, because the partitions are further divided into smaller segments, and we are spraying these segments, there is no tying down to a particular node or a particular disk. Whatever the disk that is available, I'll continue to write it, right? So that way, like, it's completely decoupled, and you can dynamically even change the number of partitions also. For example, I can go from 10 partitions to 20 partitions, depending on the traffic that has increased. Now, the new incoming message will go to the new set of partitions. The older partitions will continue to exist, but still. So you can add dynamically this number of partitions and a lot of other production-related issues that, so I have heard horror stories where the rebalancing goes for like 4 hours, 5 hours, and during which you can't do much in the system.
But how do you say that the old partitions will live and the new partitions will also live if you're partitioning by queue and you're sending it?
So like that is for the so like some kind of what do you call in the case of round robin it works, right? Yeah. But in the case of key-based partition, the new keys will get into effect after a certain amount of time only. So now if you are using it a purely producer-consumer system, it's okay because of the fact that the new partitions, because the consumption, once the consumption is done, pretty much the data is not retained, right? Only when you have a retention, then it will be an issue. So in Kafka, the partition are assigned to brokers permanently. A single partition is stored on a single node, and retention is limited by a single node storage capacity. And the failure recovery and capacity expansion require expensive rebalancing. I mean, you have to keep rebalancing the data. And rebalancing has a big impact over the system, affecting regular traffic. That is from a production standpoint. So now given that architecture, what are the programming or the messaging models that we support? So when you inject data into a stream, there are multiple subscriptions that you can consume the data from. And we support 3 different subscription models. One is exclusive subscription, another one is standby, and a third one is shared subscription. So remember I talked about some workflow related queue. That is what we call as a queuing model. So you have one new work unit and you grab that work unit. Any of the consumer can do that work unit and then put that result of the work unit into another queue so that subsequent steps can grab that, the next set of steps and move on like that, right? So you can keep on going like that. So in this case, this is a streaming model where whenever the data is coming into a topic or a partition, and then the consumer can attach to that subscription, and it's an exclusive subscription, which means at any given time only one consumer can consume out of it. Then if any other consumer comes in and tries to connect and consume out of it, he'll get an error saying that because it's an exclusive. Now, in order to avoid this, there is a standby failover case also, where 2 consumers can be in one primary, one standby. And the standby will not get any data. Only when the primary fails, the standby will get the data. And again, in these two cases, ordering is preserved. In the sense like if any unacknowledged messages are there, it will replay the messages back to the failed consumer. Whereas on the other hand, if you look at the shared subscription, if you have multiple consumers, now this data is split between the consumers. As you can see, M through M4, in the previous cases, all the M3, M0 to M4 is given to only one consumer, right? Whereas here, the traffic is distributed across multiple consumers. Depending upon the rate of consumption, some guys will get more traffic. Some guys, if assuming everybody goes at equal pace, then you will get the equal set of traffic. So this is useful for a RabbitMQ/JMS queue kind of models, where you're dequeuing work item, and anybody can do that work. It need not be ordering specific or whatever it is. And you can do even selective acknowledgement. For example, in this case, if M2 is finished, M2 and M4, it consumer one grabbed, and he said, I have finished M4 but not M2 because M2 is taking more time. Think about things like simple get a set of files that are being uploaded. I want to do virus scanning on those, right? So you can even, depending upon the size of the file, one item might finish earlier than the other item. So, but you can still acknowledge the previous item that you want. So disaster recovery. So Pulsar has inbuilt disaster recovery, which allows you to replicate the data across geographical regions. And it need not be only in geographical regions, but also across administrative domains within a single region as well. For example, I might have a production cluster, I might have a dev cluster. Now, I don't want to disturb the production cluster in any way, but I want the data coming out of the production cluster so that our developers can see the traffic and play around with it or build some new models out of it. And again, that data could be sensitive data. Some developers are allowed to do access sensitive data, or some developers have to look at only anonymized data. How do you handle these kind of things, right? So that is where all these notion of cluster, across cluster replication comes into play. So that also plays in the hands of, or that also means we have a disaster recovery in place as well. So you can produce on the same topic across multiple data centers and consume on the third different data center. And again, the consumers also could be spread around. You can do asynchronous replication, and you can even do synchronous replication too. But in the synchronous replication, you will view the whole thing as a single Pulsar cluster, and you can do rack awareness. So for example, you can say data center A is one rack. So which means one copy has to commit here, and another copy has to commit on data center B, which is another rack. Then data center C is another rack. So which means you can commit on 3 different storage nodes or whatever based on the rack awareness and get the acknowledgement before the producer at P1 says that, okay, your data is synchronously replicated. So the only thing is you need something like a global sync zookeeper. That's the only thing. It's not a challenge. Yahoo runs it. But you need to be a little bit mindful of the latency, because if the latency between the data centers is around 50 to 60 milliseconds, so if you're tolerant of that latency, you can do asynchronous replication. I mean, in fact, one of the credit card companies, when they talk to us and all, can we do sync replication? When we outlined this way, they said 50-second millisecond is easy for them. It's a okay requirement for them, but the challenge was like how to install it and maintain it. So that is a challenge. But the thing is, you can still do it. But they eventually went ahead with testing the scenarios, how we can do that. In fact, one of the things that they wanted is, so the producer one data that is being produced at data center A, it has to be consumed in the data center A. Now, but at the same time, the data has to be replicated synchronously across all of them. Now, the producer 2, which is producing, and its corresponding data has to be replicated here, but it has to be consumed there. Only when a data center failover occurs, all whatever the data that has not been processed has to be processed from this data center onwards, right? So we are working on one thing called offset replication. So what are the offsets of the data of the messages that has been processed so far? So once we replicate that, then when the consumer C2 starts at here on the same subscription, then I know what was the last processed subscription message that it did on that other data center. So but there's small delay. That 50 millisecond delay can lead to some kind of a duplication. But again, that is a trade-off, especially when you go across data centers. So it's integrated into the broker message flow, and simple configuration to add, remove regions. You can add multiple regions and other things with very simple configurations. And as I said, asynchronous is default, and synchronous replication is achievable. So then multi-tenancy. So how many clusters that Yahoo run within on the requirements? Only one cluster for 150 plus teams that they run. Because the way they have done it is they said that operationally everybody running their own cluster is going to be expensive because you have to have SREs, DBAs and other people. Instead they decide to run it as a service, which means one single cluster. And with one single cluster, you can carve resources, storage resources, like storage quotas and all. Each team gets a particular quota, and then once they have the quota, then they can manage their own quota from the application's point of view. So from that, there are notion of tenants. In this case, you will see 3 tenants, 3 teams. One is a data serving team, another is a marketing team, another one is a product safety team. Now within the data serving team, they have a microservice, which is a name application within which they have a topic. And similarly, like marketing has 2 namespaces called campaigns and ETL, and individually it will have a topic. Now, once it comes into a single cluster, can we share data across teams? Yes, you can. So you can, at the namespace level, you can say, I want to give permission to this team to access all the data coming from this topics or stream as well. So that's where authorization comes into play. All the authentication and authorization is inbuilt, and you can write your own plugins for your own internal company-wide authorization like LDAP or Kerberos or TLS or whatever it is. But TLS ships along with it. Then we also have the notion of a back pressure. For example, when producer are producing putting a lot of data in, and the consumers are not consuming as fast as, then producer can be back pressured as well. And either producer gets an error, that's a policy that you can define, or producer is held not to produce anymore until the clearance occurs, or you can dump the old data as well. And there is a backlog quota also that you can control, how much backlog that you wanted to keep it around that as well. Now, in some cases, you can even do hardware isolation too. For example, some tenant was so critical that they would have to, for example, if any monetary related, like ad serving, which is directly related to billing and all the various things, they don't want to have a different set of bookies and brokers, but they will be still under the aegis of one cluster, but the nodes are tagged, and when you deploy those topics, those will be on those particular tags of those nodes only. So that way you can still managing a single cluster, but tagged in terms of from this point of view. Then Pulsar clients are available already in multiple languages, Java, C++, Python, Go, and C. And more languages are welcome always. So the API is pretty simple. I mean, producer, just create the producer, publish it. Then similarly, the consumer also is just subscribe to a particular topic and consuming it. And keep on receiving, acknowledge. So you don't have to manage any offsets or where you left off and all the various things. So automatically it's all managed for you, so that your application becomes very simple. So because whenever application dies and comes back again, it knows where it was. As long as the application does not change its identity whenever you register itself, then automatically it will know where it left off and replay that messages from you. So then Pulsar also provides a schema registry, because we need to have streams, and the streams and topics should have some kind of a schemas associated with it to ensure type safety, right? And so we provide, if you are wanted to client to enforce the type safety, it's up to you, it's up to the application. So we don't worry about it. On the server side, we provide support as well. So it allows the schema to be maintained we have a schema registry server, which we implemented as a part of Pulsar. And the key thing is it also uses the storage, which is the bookkeeper storage, right? Or the bookie storage to store the schema definitions for each topic. So the schemas dictate what types are valid or recognized for the topic. Now, the schemas have or at the topic level, the schema consists of the name and what is the schema, which is a payload, binary representation, and what is the schema type. We support schemas for JSON, protobuf, and Avro, and also we can have some user-defined properties. A lot of times the schemas are maintained in the GitHub. Some GitHub files will be there, maintain the schemas and all the various stuff. You can add a git hash string. This schema corresponds to the git hash of whatever that string is, right? So you can define these properties and everything. Now, some schema evolution also is reasonably possible. So if no schema exists for the topic, then producer is created using the given schema. If the schema already exists and it connects with the same schema, the schema is transmitted and it's accepted. Then if the schema evolves into something backward compatible, it will be compatible to it to be tested, then accepted. Otherwise, it will be rejected as well. So now because of the schema, then SQL querying and all the various things are possible as well. So now, how much time we have? We have 10.
20 minutes. I mean, it depends on the audience is still here. If they're not walking out on you, you've got
Okay.
the room till half past. But
Okay. I'll probably 20 minutes should be good enough to cover pretty much the rest of the stuff that I have. Okay.
great.
Okay. So now we talked about the storage and message ingestion and all the various things. Now, how to process the data, model as streams. So there are multiple these things. Consume data as it's produced, which we saw, the pub/sub access pattern. We divided that compute into two different computes. One is called lightweight compute. Another one is called the heavyweight compute. So lightweight compute is quick reaction to the data and transform or react to the data as it arrives. Heavy compute is more of the traditional stream processing, where the data is processed continuously and goes through multiple stages and everything. Then finally, we also do the interactive querying of the stored streams, because of the fact that streams can be indefinitely stored, or depends on how much retention period that you have. You might want to slice and dice a stream based on time or some other criteria, right? So how can we do that as well? So if you look at a compute representation, you can represent it in the form of a abstract function, right? Incoming messages, some computation happening, then it's an outcoming messages. Now, traditionally, we have been so used to writing DAGs in the form of SQL or in the form of the DSL or whatever might be the case, right? We have been doing DAGs. So that is one, you can call that DAGs as a composite function as well, right? Now, often the tags are stitched by programmers. In the case of Storm and other things, it was much lower level. You have to write a Spark bolt and stitch them together and all the various stuff. So burden is on the programmer. Now, Spark and other people introduced the notion of DSL. Now, we're using functional notation that now if you show to a lot of programmers, say, what does that do? A lot of people scratch their heads, no, I have no idea what it is, until they figure out the functional and try to figure out all the various things. So there is a steep learning curve. So now, often these two systems, like as I pointed out earlier, messaging and the compute are in completely two different systems. This leads to powerful API, but very complicated. Like you have to tune the job, do all the various things like that. And often that is always the time-consuming part. For example, in our experience, taking a job from a developer to production takes a couple of weeks minimum, because of the fact they have to tune all the resources and all the various things before they can get to a certain reliable degree of continuous operational, right? So does everyone need to learn functional programming and configuration and management and scalable, but management overhead in terms of what knobs to turn on, what knobs to turn off. And if you are looking at IoT-like systems where you want to deploy on a single node, you have to carry along all the big, heavy frameworks, right? Like Spark, Storm, Heron, all the various heavy stuff that you have to turn it down. Instead, systems have resource constraints as well too. So from an operational point of view, multiple systems to operate, that's always a challenge which I mentioned earlier. Then IoT deployments routinely have thousands of edge systems, which makes it even nightmare when you have multiple systems. Then there's always some kind of impedance mismatch or duplication of functionality between systems, because each projects and each systems are developed by different teams, and they always have the tendency to diverge, and each one not trampling on each other, and which one you use and which one you not use, right? And this always creates a developer and operator friction. So what are the lessons that we learned so far in the streaming world? I mean, we talked to a lot of companies, and we also looked at all the Twitter workloads and everything that we did. And when we talk to them, I mean, this is what most of the 80% of the workload that people do. Data transformations, data classifications, data enrichment by talking to some external systems, and data routing based on some content, then data extraction and loading, and some simple count, min, max, those kind of aggregations, and some kind of simple microservices. So significant set of tasks are exceedingly simple. Now, can we address, instead of addressing these significant simple tasks with a heavy hammer, can we do a simple hammer for that? So that is where we took inspiration from serverless. So if you look serverless, like Azure functions and Lambda functions, it's all simple function API, and functions are submitted to the system, runs per events, and there's a composition API that can do some complex things, which is kind of rare, but it's widely popular as well. And if you look at the shades of differences between the two, there are some similarities. Both are event-driven architectures. Both can be used for analytics and data serving. Both have composition APIs, one in the form of DSL on the streaming side. Another one is the configuration-based for serverless. And serverless typically does not guarantee ordering, because more of a queuing-like systems. Whereas, and serverless is pay for action, and serverless gets triggered based on event. Whereas stateful streaming system have the notion of a state, like aggregation and other things, and the state has to be provided again in the invocation. Then also, like the stream processing jobs are always running, or the functions are always running, right? So those are the states of differences. So that's why we added more like serverless, but with the streaming enabled, what we call the stream native compute using functions, applying this insight gained from serverless. Simplest possible API, support for multiple languages. Currently Java and Python are supported. And use the native API. I mean, you don't try to reinvent a lot of things. If very simple API, most of them comes from a native language API and of the language itself. And it also scales the developers. From a productivity point of view, from day one, write Java programs, people can go and write it very quickly, right? Then rather than reinventing new concepts, use the same message bus native concept, like input as output as topics. And of course, we have a flexible runtime, which I will show you in a few slides later. So how do you write a simple function? That's it. You just inherit from a Java function, and this is what you do. So now your input is nothing but a one topic, and the return from the function is an output topic. So that way what happens, all it does is take this input string that is coming in, adds an exclamation, and returns out. So, and when you, the same function, when you compile as a jar and submit to a system, at the time you give what is the input topic and what is the output topic for this function. So that's all you need. And the same function code can be reused on a different set of topics too. So that way, and also like the same function can be written on multiple instances, which means like 10 instances of this function has to be run, because the sheer size of the topic data coming from the topic will be pretty high. So this is SDK-less. If you wanted a simple SDK, then you can derive from the Pulsar function, and it has an extra context, which is for the state. So across invocation of the function, you have the notion of a state that you can store and retrieve it whenever you want to.
How does that context deal with scale up? Or like, do you ever scale up multiple copies of that function? And if so, how does it deal with that context?
So that context is there is a distributed state. This is a local state. This local state is essentially for the same function instance, which I want to remember something that I did so that I can access it back, or that is one state. Another state is distributed counters. So that I will talk to you in a couple of slides down. So the Pulsar function is executed for every message of the input topic, and it's not only one topic and one input topic and one output topic. You can take data from multiple input topics and can take data out from data output can be multiple topics as well. So, and output topic can be an avoid topic as well. I don't want to return anything too. So again, serialization and deserialization, you can plug in your own custom serialization as well. And the key thing is it integrates with the schema. So that functions knows about what is the schema of the topic that I'm getting in and all that stuff like that. So processing, we provide all the processing guarantees. Again, at runtime, you can change it. So controlled by whenever you submit the same function, I want effectively once or exactly once or at least one semantics. You can doing this. You don't have to code separately for stateful versus non-stateful. So how does the functions get deployed? You can deploy in the broker itself, or there is one extreme form where it can run as a thread within a broker itself, but that is very similar to the object relational folks. They were using the abstract data types and the corresponding operations in the C code of the server itself, right? You can deploy it like that, or you can run it on the same node but a different process, or it can be run it on a separate set of worker nodes where you can run them separately. And the workers in turn distribute the function instances. As you can see, you have transform functions, 2 or 3 of them are running. Then data route function is only 1, whereas function word count is 2 of them running, right? So you can scale up the functions and scale down the functions also. Not automatically yet, but manually you can scale up and scale down. Then you can even do deploy on Kubernetes. Kubernetes will be running as pods. So in this case, as you can see, like function data route has 1 instance, function transform has 3 instances. And these pods, function deployment pods are thin pods, actually. So the built-in state management in functions. Functions can store state in inbuilt storage. The framework provides a simple library to store and retrieve state. And you can do counters also. For example, you can do a context.increment counter. This is a global state. So you can keep on getting the word and increment the count, then the count gets incremented.
So how do you ensure that you don't lose that state on failure?
This is a global state.
What's that?
This is a global state. Because remember, underlying storage is distributed and replicated, right?
Yeah.
So because of the fact, even if a node goes down, the state is available in another node.
But does that mean that, like, for each counter bump, you're doing a push to storage?
Yes.
Okay.
And since our writes are faster through the journal and all the various things, so we debated about local state versus global state. Then you find out, like, I'm okay with the small performance hit. I'm okay with being on a global state because local state can be used locally, but when the node failure occurs, then recovering that state in a global takes some amount of time, right? So that way, like being everything global made life easier for us. So, so this is again data in and out. I want to go into these details, essentially like how to get connectors for data in and data out of Pulsar. So we have a lot of connectors in terms of Cassandra, MongoDB, and all the various things like that. Connectors also use the function framework. So for syncing data in and getting data out. Again, they can be run in the form of brokers. So it provides fault tolerance because execution of the I/O itself can be, when a node goes down, the execution is moved to another place. And then it also can have parallelism, and it can increase and decrease for elasticity based on manual intervention. It can load balance also. Then on demand, you can update the code as well too. And finally, like interactive querying of streams. So now, if you look carefully, the 2-level architecture that we had, so the bookie nodes, the storage nodes, they are doing write-throughs, but not a lot of reads going on because of the fact most of the data is served out of the cache itself for a producer-consumer environment. For catch-up reads, occasionally catch-up reads will come, and some occasional reads will come when there is a broker failure. So that is the time that you have to reconstruct the state of a particular failed broker, right? Other than that, the read part of the bookie is not even used at all. And similarly, the network out of the bookies itself not used as well, or the storage nodes are not used as well. So what we did is so we took Presto. How many of you know Presto? So Presto has these nice connectors to underlying storage engines. You can write your own connectors. Now we run. So we wanted to exploit the non-usage of CPU on the storage nodes. So because it's hardly used 10% or 15% at the max. So we run the Presto, the worker nodes on those individual storage nodes. And then there's a coordinator. Then we did a connector that connects directly and reads the segment out of the book keys itself. So now whenever a query is issued, all here it has to go with this, consult the schema registry, which is already there, which gives the schema for the SQL, and also consults a broker to find out where the segments are for that particular topic or the stream. So then all you got to do is bring that segments and query them. Or you can even slice it by ingestion time. Okay, I want the data from time T1 and T2. So you can indicate as a part of the query itself. And those are all inbuilt attributes that every ingestion will happen. Then now, once it is there, then Presto reads the appropriate segments and gives the results, and the coordinator does any aggregations and everything that you need to do. And so which means you can interactively query that stream. The key thing is when the message is published, it is immediately queryable within a second or two. Because the data from the journal goes into the tiered storage within a second or two. So once that moment it reaches the ledgers, immediately that becomes queryable. So people who are interested in doing near real-time queries where they're refreshing dashboards or whatever it is, they can repeatedly run the queries on every minute basis or whatever, still they give the effect of this thing. And this also is very useful when you have auditable logs, where you want to audit the financial transaction that has flown through the system. You can keep on all the data. It's not a lot of query load that is going in, but an occasional query load that can come in, and you can query them. Now, my team also came with idea of how to create secondary indexes on this. So they are looking at a way to create a what called index topic, and for every message that is being created, if the particular value, what is the attribute value that you need to do, it will be injected as a separate stream, and that will be stored. Now that topic will be very small enough, right? So pre-read that topic or cache the topic so that you can now all the message pointers, then grab all the segments. It gives you a kind of secondary index as capability as well. But we have not done it yet, but that's a thought process behind it. But if you have better ideas, happy to share. So from a Pulsar performance point of view, like we are pretty high, like 7x faster than Kafka. That is based on the open messaging benchmark. There's open messaging benchmark that if you type open messaging /benchmark, we kind of put out some measures of, I just was picking a couple of numbers and showing it, but it has a bunch of numbers that you can take a look at it. And if anybody interested in benchmark, let me know, then I can already like Alibaba, then a few companies have joined the open messaging benchmark or open messaging initiative itself. We're happy to.
Is this per node or per cluster?
This is on a cluster of 3 nodes with a single topic and things like that. I mean, I didn't know the full details. Full details, I think like 1K messages, 1 topic, and 1 publisher, 1 consumer. Try to see how much fast we can go. Then again, Kafka's latency is pretty jumpy when it comes to rebalancing times, whereas ours is kind of also is consistently less than 5 milliseconds. Now we have a special edition of Pulsar that we go with the financial customers, which is like 200 microseconds. That we avoid a lot of mutexes and by doing busy waits and all the various things like that to reduce latency. That latency is end-to-end 250 microseconds, or sorry, 200 microseconds. And we can even get it down. The dominating factor is the kernel at that point, not the Pulsar, this thing, and the network and the kernel are the dominating. So if you do special hardware like NVDIMM or things like, I mean, we used NVDIMM as a journal, because for journal, in order to keep flushing as fast as it could, we used NVDIMM. For networking and the kernel bypass, if you do some cards like SolarFlare or network bypass cards, we can get network probably down to a couple of microseconds. So that's all I had. So if you wanted to know, a lot of people ask about what is a Kafka versus Pulsar, then these are the various differences. It's a laundry list, but its durability is a big difference. Multi-tenancy is a big difference. Tiered storage, hot warm data migration, zero application out of the box, and cluster expansion is seamless when the system is operation, and unified messaging model where you can consolidate multiple different systems like RabbitMQ, JMS, and Kafka-like systems into one single system. In fact, one of the Chinese companies called Zhaoping.com went into production a couple of weeks ago, and one of their this thing is we have RabbitMQ and Kafka and all. We don't want to manage these two systems and all. They just collapsed everything into one single system and went into production with it. Then another thing that I didn't mention is because of the fact that you have multi-tenancy, each team can create several topics, and that is where you can support millions of topics. So currently, like Pulsar runs at a high scale around 2.3 million topics, so which means essentially 2.3 million streams you can support. I mean, these are some of the companies. I didn't put all the lists. Around 25 plus companies have gone into production with it, but so there is one use case that I thought I'll discuss it, but let me see. This is an interesting use case actually from an IoT world. So the industrial IoT. So like typically like you have the edge systems. Now with Pulsar you can run on an edge box. It's a reasonably sized edge box. One of the projects that we are working on, it's a curious project to get Pulsar running on what do you call a Raspberry Pi. So this is an edge box which sits on the manufacturing floor or a factory floor, and so then the data is coming from multiple sources from the assembly lines or the sensors out there, and there are some entities that are talking proprietary protocols on those sensors and getting the data and ingesting data into the Pulsar actually. And the edge box, the company has made run a Kubernetes on top of the edge box, and they're running a one pod of Pulsar itself. So Pulsar can, when you deploy Pulsar in a very low edge, you don't need the separation of bookkeeper and all the node bookies and brokers, right? Instead, you can collapse all of them into a single process called Pulsar standalone. When you do Pulsar standalone, it collapses all of them into one single process, and one single process is what you get. Even Zookeeper also not needed. Zookeeper also integrated into the whole mix. So you can do functions there. So the need for doing functions there is, okay, I'm getting this lot of data. Do I have to send all the data up to the cloud to process it? So you can pick and choose what data you want, or you can transform your data into a common things you want right there on the edge itself. Then we have the notion of geo-replication for data movement, right? So that allows the data to move from Pulsar to cloud. And you can do it to multiple cloud because of the fact mesh replication. You can do multiple data centers, and each one can send the data. And there you can write a complex data coming from all the edge boxes coming deployed on the manufacturing factory floor to give analytics about how the entire factory, multiple lines are working, not only in a single factory, across multiple factories and everything, right? This is one use case we are working with the company, and they are getting this up and running. Probably they already have run it once, but they're adding some device-specific protocols and everything to be ingested in Pulsar as well. So this is, we ended up in this use case because we didn't anticipate this one at all. So, but the geo-replication serves as a data movement here. So that's all I had. Any questions?
Yeah, one question that I had, what kind of guarantees do you provide? Like, if you're a client and you want to make sure that your readings make it into the stream, and also that you've received every element of a topic that you're interested in. Like in the face of failure, both on the client and the server, how would you ensure that you send everything and receive everything?
So the Publisher also gets the notion of what do you call when you send it, your data is guaranteed that it's persisted unless you get an acknowledgement. Similarly, consumer also, when you consume the data, you have the notion of acknowledgement. So when you consume data point on message 1, you have to acknowledge message 1. Then only you can say that otherwise what our offset is for this. So let us say you are saying, I am client A, because that is your ID or uniqueness.
Is this something that goes in the client code, the acknowledgement?
Yes.
And,
The client library, not in the client identifies itself as a name, whatever it is.
Yeah.
Then the client library handles all of this. So now all you have to do at the application level is once you process the message, you tell me that the application is done. Now the thing is like in producer, we can guarantee exactly once because using message IDs and sequence IDs and all the various things, we can dedupe the messages. Now on the consumer side, it's hard to do exactly once delivery. Like that is the nature of the beast itself, right? When you consume, I finish the processing of the data, but how do I know when the acknowledgement has reached, I not have reached? So the only thing, the consumer has to take care of it itself, what time it processes and other things. Yeah. So if you wanted to do a beam like the stateful processing, Pulsar is an ideal client ideal engine to do beam thing kind of things. Like for example, this has the storage for storing state as well as late order processing and all the various things. It also has a notion of ingestion. So for doing something like, this has been one of the challenges that we had at Twitter. We have been conjuring a lot of things, putting together, but we never had a clean system underneath in order to get the top level framework work seamlessly well, right? And this could be one of the systems that can power the higher level frameworks like Heron, Beam, and all the various things. And in a fashion where you have a way to unify all these guys. So
yeah, this strikes me as, basically by you've gotten rid of Kafka. You've taken Kafka out of the picture.
Kafka out of the picture, Hadoop out of the picture too.
Yeah, and I'm sorry?
Hadoop also out of the picture. A lot of people use Hadoop for the state storage, I saw.
Yeah.
And you wanted to take out the key value store also out. So that is in the works. So that's why I'm trying to talk to Badrish about doing Seek faster.
The faster, I take it.
Yes.
Yeah, okay.
Okay.
No more questions, then let's thank the speaker. Thank you.